All right, this morning we're talking about exponential decay. Now yesterday we were talking about exponential growth, and we should realize that any exponential function has x in the exponent. All right, now yesterday we were talking about exponential growth. Does anybody remember what made that function growth? Why our graph went up and to the right yesterday? Okay, the a can't be 0, perfect, and something else about the b. Yep.
Wasn't it greater than
The b always had to be bigger than 1. Every time we looked at an exponential function yesterday, our b value was bigger than 1. That makes it growth. That means that my graph is going to go up and to the right. Now today, we're going to look at an exponential decay function, and it's still going to have the form y is equal to a times b to the x. It's going to look exactly the same, except the a this time has to be bigger than 0, and my b is going to be between 0 and 1. So my b values today are going to be like a half, or a third, or 3/4, or 0.8. They're going to be somewhere between 0 and 1 to be an exponential decay function. Now, when it's an exponential decay function, that b value is called the decay factor. The decay factor. All right, now, as I look at our parent function, y is equal to a times b to the x, we should know from yesterday, what does that a value do? What does that a value do? What? Okay, opens it up and down, and? Beautiful. All right, so that a value causes a vertical stretch or shrink. And if the a is less than 0, if it's negative, there is a reflection over the x-axis, which is y equals 0. Remember, y equals 0 is the asymptote. Y equals 0 is the asymptote. So on this graph, I'm going to have an asymptote on the x-axis at y equals 0. We're going to put that dashed line. It's going to work very similarly. Y equals 0 is our asymptote, a line that our graph gets closer and closer to, but never touches. All right, now as I'm looking at this, remember that what is the first point from yesterday that I was able to graph? 0, 0a, because what is at 0a? The y-intercept. Okay, so our y-intercept is at 0a. That's not going to change today. That pattern's the same. So if I go up a distance of a, my y-intercept is at 0a. Okay, now what is the second point that I get? All right, another point that I get is when I put in 1 for x, b to the first is b, so my y value is just a times b. However, this is exponential decay. It's not growing from left to right. It's going to be falling from left to right. So with exponential decay, I'm going to go to the right one, and I'm going to go up a value of a times b. So this is the point 1, comma a times b. The curve with exponential decay, when my b value is between 0 and 1, that graph, that curve, is going to be falling down and to the right. And it gets closer and closer to that x-axis, but never touches. Now, what's my domain? All real numbers. Anything where x is in the exponent has the domain of all real numbers. And on this graph, my parent function, what is the range? What? All right, it's above that line, y equals 0, so my range is y is greater than 0. Anybody have an issue with that? Okay, let's do one of those together, just very quickly to review, and then we will move on from there. So let's take a look at our A. Part A, y is equal to 3 times 2/3 to the x power. Now remember, x is in the exponent, the form is always y is equal to a times b to the x power. X is in the exponent, my form is always y is equal to a times b to the x power. All right, what's my a value? 3, and what's my b? 2/3, perfect. All right, where's my first point? Where is the first point that I'm looking for? All right, my y-intercept is always at 0a, so that's at 0, 3. All right, so I'm going to go up 3 and make my first point. All right, then I need to get another point. All right, Nick, where do I get my other point from? All right, the x is 1, the y is a times b. So 1, comma, my 3 times 2/3, and 3 times 2/3 is what? 3 times 2/3? 2, perfect. So I'm at 1, 2, so I go to the right one, and I'm up 2. Now, we should realize, or we should know, that my graph has a guide, and that guide lies where? The x-axis, absolutely. My asymptote, the guide for my graph, is on the x-axis. It's my asymptote. So I'm going to put a dashed line for that asymptote. It's a guide for my graph. It needs to be on the graph, but it's not part of the graph. So my asymptote lies on the x-axis, which is y equals 0. Always need to make sure my asymptotes are on my graph. And then exponential decay, my graph falls down and to the right, getting closer and closer to that x-axis, but never touching. And never going below that x-axis. All right, what's my domain? Cody, what's my domain? All real numbers. My x's can be anything they want when x is in the exponent. And Tanner, what's my range? All right, I'm above the x-axis. I'm above the line y equals 0, so y is greater than 0. Really, I mean, the similarities from yesterday should be abounding. They're everywhere. Except, what makes it decay? What makes this graph fall down and to the right instead of going up and to the right? The b. When my b is between 0 and 1, it falls down and to the right. When my b is bigger than 1, it goes up and to the right. That's the whole picture. All right, now let's add in our component of y is equal to a times b to the x plus h minus k. Oh, I've got a major typo there. That should be x y is equal to a times b to the x minus h plus k. Very big typo there. B to the x minus h plus k. Now, my a value is still doing exactly what it did before. So that a value is a vertical stretch or shrink. And if the a is less than 0, it's a reflection over the x-axis. All right. What does h do, folks? Moves it left or right. So my h is a shift left or right. Remember, it's the opposite of what is with my x. And my k value does what, folks? Moves it up or down. So it's a shift, a translation, up or down. Very nice. Any questions so far? All right, let's do one more graph. Just really want to make sure that we know how to graph these. All right, so where do I start? Where do I start when I have an h or a k, or an h and a k involved in the situation? What do I start with? Nick? Okay. Logan? You're going to start with the parent function. Remember, I always want two graphs on these. I always want two graphs on these, so I'm going to start with the parent function. Remember, you will not have a graphing calculator to graph these on Friday. All right, so I'm looking at my parent function, and the parent function is always everything up through the x. Everything up through the x. So in this case, it's going to be y is equal to 2 times the quantity of 1/3 raised to the x power. All right, what am I looking for first, Ryan?
The
0, 2, because that is the y-intercept. Okay, so my y-intercept is going to be at 0a, and in this case that's 0, 2, because my a value is 2 and my b value is 1/3. Now I need to make sure that I really tune into the fact that, okay, my b is 1/3. How is this graph going to look? Is it going to go up and to the right or down and to the right? Down and to the right. My b value is 1/3. It's between 0 and 1. It's going to go down and to the right. Okay, so 0, 2 means I go up 2 and I make a point. All right, Alex, what do I do next? All right, another point I'm looking for is at 1 and then a times b. So that's 1 comma, let's see, my a is 2 times my b of 1/3. So that's 1 comma what? Perfect. At 1, I'm at 2/3. All right. Now, what else do I need on my graph? What else do I need on my graph? The asymptote at y equals 0. So I'm going to get that asymptote on there on the x-axis at the line y equals 0. And my graph slopes down gently towards the x-axis. Now, I know that these 2 points are pretty close together, and they don't give us a great picture. I mean, I could put in -1, 1/3 of the -1, flip that fraction is going to be 3, and 2 times 3 is 6. So that means at -1, I'm up at 6. Always nice to get a nice idea of what that graph really looks like. So at -1, I'm up at 6 with my parent function. So it comes down and approaches that x-axis, gets closer and closer and closer to that line of y equals 0, but never touches. Okay, now, am I finished? No, because the function that I'm really looking at is y is equal to 2 times 1/3 to the x minus 2 plus 1. So my question is what does this minus 2 do to my graph, and what does the plus 1 do to my graph? All right, what does the minus 2 do to my graph? Right 2, perfect. And what about plus 1? Up 1. Any questions so far? Okay. All right, now what am I going to move first? Move your asymptote first. It's the guide for your graph. Move that asymptote first. Move it right 2. What happens? Asymptote's not really going anywhere. Right 2 doesn't do anything to that horizontal line, but up 1 sure does. So I'm going to move it up 1, and now my asymptote is at what? Y equals 1. Okay, so my asymptote for the entire graph is going to be y equals 1. All right, then I am going to take each point and shift them right 2, up 1. So I start here, right 2, up 1. Right 2, up 1. Right 2, up 1. And I'm going to gently make that graph. It approaches the line of y equals 1, but never touches. All right, Sydney, what's my domain of this graph? All real numbers. X is in the exponent. I can always do anything I want. What about my range? What about my y values, Anna? Y is greater than 1. We're above that line of y equals 1, so y is greater than 1. All right, one more thing we've got to make sure we know is always our y-intercept. All right, what am I going to do, or where does my graph cross the y-axis? What is my y-intercept? Which graph am I looking at? I'm looking at that blue graph. Where does that blue graph cross the y-axis? Where does my blue graph cross the y-axis? It's not on the graph. That creates a challenge. It's not on the graph, but what do we know about our y-intercept? The x is always 0. The x is always 0. So we're going to go to our function. Y is equal to 2 times 1/3 to the 0 minus 2 plus 1. All right, now, you can use a calculator, but I'll be honest, folks, you shouldn't need one. You shouldn't need one. So this is equal to 2 times 1/3. 0 minus 2 is negative 2 plus 1. What does a negative exponent do to a fraction? What does a negative exponent do to a fraction? Flips it. The stuff in the top is going to move to the bottom. The stuff in the bottom is going to move to the top. A negative exponent flips that fraction. So that's going to be 2 times, 1/3 flipped over is 3 squared plus 1. All right, 3 squared is 9 times 2 is 18, and 1 more is 19. So my y-intercept is 19. We should be able to calculate our y-intercept in any case because we always know that the x is 0. Anybody have issues with that? All right. Let's take a look at an exponential decay model. Yesterday we had our exponential growth model. Y is equal to a parentheses 1 plus r to the t power. Today we're going to look at an exponential decay model. An exponential decay model is when a real life quantity decreases by a percent. If it's going down by a percent, we're looking at exponential decay. If it goes down by a percent, we're looking at exponential decay. Each year, the amount y of the quantity after t years is modeled by this equation. Y is equal to a, parentheses 1 minus r to the t power. So when it's growth, it's 1 plus r to the t. When it's decay, when it's going down, it's 1 minus r to the t power. Now, remember that a is still your initial amount. That a is still your initial amount. That r is still your percent decrease. Is still your percent decrease. And remember, it has to be written how? All right, got to write it as a decimal. And t is the time in years. Also, just one comment, if they ask you what the decay factor is, your decay factor is always 1 minus r. So your decay factor is always equal to 1 minus the r. Your growth factor was 1 plus the r. Your decay factor is 1 minus the r. Good so far? Ladies, gentlemen? Perfect? All right. So here we go. How are we going to use this? A new car costs $25,000. The value of the car decreases by 15% each year. All right, write an exponential decay model giving the car's value y in dollars after t years. Estimate the value after 4 years. Okay, now, the first thing you need to clue in on, because I'm not going to tell you if it's exponential growth or decay on the quiz on Friday or on the test. The first thing you need to clue in on is you say, okay, the value of the car decreases. Okay, it's going down by 15%. It's decreasing by a percent. It's going down by a percent. Your automatic gut reaction has to be, okay, that's y is equal to a, parentheses 1 minus r to the t power. You've got to know which equation you're going to use. And this is the third equation now this chapter you need to have memorized. So if it's going down by a percent, it's y is equal to a, parentheses 1 minus r to the t power. All right, so let's set this up. Y is equal to, what is my a? What's my initial amount? What's my starting amount? 25,000. Parentheses 1 minus, what is my r value? 15%, but we're going to change it to a decimal, so that's 0.15 to the t power. Fancy. Fabulous. Not fancy. Fantastic. All right. What's 1 take away 0.15? What's 1 take away 0.15? 0.85. Okay, so y is equal to 25,000 times 0.85 to the t. Now, I do want to take a second so for you to understand what the 0.85 means. If I take away 15% of the car's value every year, how much value does the car keep? I took away 15% of its value, but how much did it keep? 85% of the value. And we want to know what the car is still worth, so we want to know what value it still has, not what got taken away. Does that make sense? Okay. All right. Now, what am I going to do to find out, to estimate the value after 4 years? Yep. All right, I'm going to replace the t with 4. So y is equal to 25,000 times 0.85 to the 4th power. All right, very quickly in your calculator, go ahead and take 0.85 to the 4th and then multiply it by 25,000. About how much is that car worth? About how much is that car worth? Anybody have it? 13,050.15. Okay, it goes to 156. Okay, so the car, we're going to round appropriately, is worth about $13,050 and maybe 16 cents. Are we okay with that? All right, now we want to make the graph. I told you yesterday, application problems, I would prefer you use a grapher. All right, so let's go ahead and look at this graph in our grapher to make sure that we all know what we're doing. Okay. All right, turning it on, clearing out what's ever in there, going to y equals. Clearing out whatever it is you have in there. All right, as we look, we're going to look at y is equal to 25,000 multiplied by 0.85 raised to the power of, so caret key, and to the x. All right, now let's go to window because we got to make some thoughts. We got to make some choices about what we're talking about here. So if we go to window, my x's, well, x's are really what variable? I use x because that's what my calculator has, but really the formula says we're going to use what variable? T. Okay, now t is standing for what? Time. So approximately what do we think would be a good smart choices for values for t or for x? Starting at 0, time starts at 0, maybe up to what? 5 years? I'm talking about time of a car, right? I mean, you might keep a car for 5 years, but what would seem reasonable for the life of a car? 0 maybe up to, I mean, are all cars in the junkyard after 5 years? 10 or 20 maybe? Let's do 20 just to get a good picture of our graph. Fair enough? Does that make sense? Now, you might not keep your car for 20 years, but somebody might have that car for 20 years. Okay? 20 years is a pretty old car though, but that's okay. All right, scale is going to be 1. Now, what is the Y value talking about? Price of the car, okay? Which is going to start where? 0. And go up to at least how much? Okay, it starts at 25,000 and it comes down from there, right? So I need to have my graph go up to at least 25,000. So let's cheat, let's do 26,000. And we're going to let each tick mark be 1,000. Okay? All right, let's look at this graph. I'm sure it's beautiful. Oh my gosh, look at that. Amazing. All right. Thank you. All right. So, as we look at this graph, now what are we going to put on our homework? Okay, so I got this graph paper over here. I'm going to put my scale. So I went from 0 to 20, and I went from 0 up to 26,000. Okay? My graph looks sort of like this. All right? It's a good estimate. It's not perfect. I'm not going to deny that it's not perfect. But now, what do I want to know? Okay, now I want to know, use your graph to estimate the value of the car, when the car will be worth $8,000. Okay, you got a couple options. You could go to trace, and you could just keep putzing around here to see when you get a Y value of $8,000. There's a better way, easier way. Go to second trace to calculate. Oh, I'm going to lie. Let's go, get out of there. Go to Y equals. Go to Y equals. I want to know when the Y is how much? 8,000. So my second equation, I'm going to put Y equals 8,000. Now look at your graph. Where is my answer? Where is my answer? Where they intersect. Absolutely. So I have this line coming across. I have this line coming across right here, and we know that's at 8,000. And my solution is going to be where they intersect. My solution is going to be where they intersect. Now, where do I go to find the intersection? All right, second trace to calculate. And I want to calculate what? Where they intersect, number 5. First curve, enter. Second curve, enter. Guess, hit, enter, and watch the magic. All right, so we get the point. X is about 7.011 when the Y is 8,000. Now, what is that telling me?
7 years.
Beautiful. Approximately 7 years, the car is going to have a value of about $8,000. Now, when you think, I mean, this is realistic, folks. When you think about that, that's amazing. In 7 years, you lost $17,000 in the value of a vehicle. Cars are expensive items, and they do not keep their value very well. Any questions on this? Any questions on this? All right.